Good morning.
Good morning, Doug.
Those desiring to touch infinity are in the house. So let's touch infinity. All right, I'm sharing a screen and looks like that's going well. Bam. Man, yesterday was a great day. Except for that, had a slight slide into the dirt
Oh man,
mountain biking.
no pain, no gain.
No pain, no gain. Yeah, it's totally worth it. It wasn't even my fault. It was a bike malfunction. Whole back axle kind of came unscrewed. I didn't realize that the type of axle it was. It's a mountain bike I just bought, and the back wheel came off and just skidded to a stop after a jump I went over, and I flew over the handlebars and landed in the dirt. Yes. All right. Here's your warm up. If that square, I'm going to give you a second to think about this. I hinted at this or gave you a question like this the other day. If that square was 1 by 1, then what is the area I have shaded? Obviously, I started with the original square broken into quarters, and so I shaded a quarter of it, and then broke that quarter into quarters and shaded a quarter of that. So basically, to start with, you have a quarter, and then that would be plus a 16th. What's that area? If it never ends, it's not hard to get this if I ask for the first 12. But what if it never ends? Give you a second to think about that. We'll say this is 1 centimeter by 1 centimeter just to give it units. Forever. I bored my wife with a short discussion about this business in the car this weekend. And she quite logically, and this is probably the last day we'll talk about this, but she quite logically said questions of this nature are infinite because you're always adding more. The area is never gone and you're always adding more. So we didn't use the language of our class, but she thought it was divergent, meaning it doesn't approach something
But obviously the area can't be greater than 1 centimeter squared, right? Because the original square is 1 centimeter squared, and it's only part of that.
Yeah. Yeah, that's well said, Vale. That's an excellent way to look at this. Like it can't be more than one, right? So how could it be infinite? It can't be more than one. Look at all that white. It's never going to get outside of that, right? Can't get any bigger. So I'd say that's an excellent, just kind of a logical, simple argument, Vale, that I didn't think of. That it can't be infinite. So maybe it takes a second to kind of get going on this, but if you recognize that this is a fourth and this is a fourth of a fourth and this is a fourth of a fourth of a fourth, at some point you realize the problem is 1/4 plus 1/16 plus 1/64 plus one. Oh geez, what's the next one? 24, 128, 256, is it? Yeah. 256 plus dot 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 forever. Again, that dot dot dot's extremely important in this class. As far as the language of this class is concerned, if you decided to stop right here in the language of series, and I've already introduced this a little bit, but that would be S of, well, not N, but 4. Because I'm just saying, just add the first 4 up. It's not really an infinity problem if you add up the first 4 or the first 40 for that matter, or the first 400 million. If you stop, this isn't that complicated of a problem other than very time consuming. But the dot 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 part then is really, again, mathematicians would take issue with this statement. They would say you can't say the sum of the first infinity because it's not really a number. Mathematicians would say S of n, and then they'd say, what's the limit of this as n goes to infinity? Because infinity is not a number. And so, fine, okay, I get that. But of course, the key to this, as I've been discussing a little bit with you, is to recognize what kind of a series is this. Notice you're adding them, so it's a series. This is the most common type of series and a big part of really 10.3's discussion. What kind of a series is that?
Recursive, right?
It's recursive in the sense that each term, and I'll write it this way this time, is found by taking the previous term and doing what to it?
Quartering it.
Yes. So recursive is where you just describe how to get the next one. So there's a pattern, in other words. So I recognize the pattern to it. Incidentally, I wonder if you could write the formula, or I wonder if you could write the series out. Let's take a second and do that. It's the sum of, let's see, it's 1/4 to the n, does everyone say n? Yeah, I'll say n, to the n power, and that would be if n started at 1 and went forever. Do you agree with that? Is that a true statement? Is that the same as that green series up there? Again, notice I'm saying the word series today, not sequence. Sequence is the numbers with a bunch of commas. And now from now on, we're going to start adding them together. So 10.4 is, or 10.3 is talking about a series, add them together. So that's the summation symbol says add them. So that'd be 1/4 to the 1, that'd be 1/4. And then 1/4 squared would be 1/16. Yeah, that's actually true. Let's see, could you also start at 0? This is the one thing I'm a little worried about with respect to your thinking on this subject. Could I start at 0?
You could, but you'd have to have plus 1/4, but that would mess up all the other ones.
Nice. Yeah, you'd have to, like, it's missing a fourth. In other words, if I said this, 1/4 to the 0 is 0. So you could do it, but you'd have to have like another 1/4 out front. That's kind of the direction you were going with that, Raymond. It's like it needs a 1/4. And so if I just gave it one more 1/4, there, now you have 1/4 times 1. And then when you put 1 in, you have 1/4 times 1/4. So I just kind of added a 1/4 to it. So that's both true. So basically every term is found by multiplying the previous one by 1/4. And anytime you're multiplying by something, that's a geometric series. So that's the $1 million word I want you to see here. And at this point, these are cool because, and I've showed you this before, there's actually a way to literally add these up. This genuinely does converge. Geometric series will converge if your R value, in this case, 1/4, is less than 1. In other words, each one is getting smaller and smaller and smaller. It's kind of like thinking of it as 25%. Each one is getting, it's just 25% to the previous one. So they get smaller and smaller and smaller. In other words, the sequence of numbers is on its way to 0. By the time you get way out there, they're on their way to 0. Therefore, if you add them up, they might actually add up to something. In the case of a geometric series, they do. And as I said the other day, you could go into Excel and add up the first even 20 of these and probably guess where this was going, but we don't really have to guess. And this is the thing I want you to really understand well. If I say S is equal to 1/4 plus 1/16 plus 1/64 plus goes forever. And then I take that multiplier 1/4 and I multiply both sides. I make a new equation, a second equation. I was talking with Martin about this after class last time because he was like confused at how this was working. So I'll just highlight it. It's important to understand that this is a second equation now. If I take that first equation and multiply both sides by 1/4, notice this first 1/4 turns into 1/16. That 1/16 turns into 1/64. And that 1/64 turns into 1/256 and so forth. So now I have two equations. And if I subtract them, I'm going to subtract them this way this time. By the way, can you subtract two equations? The answer is no. You can subtract the same thing you want from both sides. So over here, I'm going to erase this, but over here, could you, this is just a technical point, but over here, could I subtract 1/4 S from that side? Yes, as long as I subtract 1/4 S from the other side. That you can do, right? It's okay to subtract the same thing to both sides. But hey, look, those are equal to each other. So since the right side of this doesn't look anything like 1/4 S, and the right side of this does, then I'm sort of going to replace it with what it's equal to. So we're subtracting these two equations, but it's really just subtracting the same thing to both sides, from both sides. I don't know if that bothered any of you. I hope it did actually, but. So I'm subtracting these two equations. Well, what do you get? You have S minus 1/4 of S, which I'll take the time to rewrite. And then something very beautiful happens on the other side. And this only happens because it's a geometric series. Remember, that's the only one of the simple things you can do to both sides of an equation is multiply it by something. And notice I get the exact same equation, or I get the exact same series on the other side. Well, not quite. What happens over there? This cancels, that cancels, this cancels, cancel, 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 cancel. This guy is left behind. So there's really just a 1/4 over there. Now I don't have infinity anymore. I don't have infinitely many terms. And so if I take 1S minus 1/4 of S, I have 3/4 of S. And then if I multiply both sides by 4/3 to get rid of, to solve for this original S, which is what I wanted to know in the first place, 1/4 times 4/3. Bam, the 4's cancel and I get 1/3. Isn't that kind of cool? So the area is not infinite and it is exactly 1/3. Now, can you ever get it to be 1/3? No, because you can't add infinitely many terms. You never get to be done. But the idea is it approaches a limit. Even though you're adding infinitely many things, it doesn't get over 1/3. From the discussion on Thursday, does it approach that by oscillation or monotonically or monotonically? I don't even know.
Be monotonically.
That's exactly right, because it starts out at 1/4 and it works its way higher to 1/3. Does that make sense? It just gets closer and closer and closer to 1/3 from the bottom. And so we say in calculus, we have less trouble with this in calculus because this is now Calc 3 with this idea of things getting infinitely close to things. So we've been playing with this idea of infinity for quite a long time, and that's what calculus really does. And so we can literally say this adds up to 1/3 if there are infinitely many terms, if we go infinitely long. And so it's just kind of cool. So this business of a geometric series, this is one of the few series you can actually add up and get an answer for.
Just out of curiosity, when we write this in notation like S of n as n approaches infinity, do we have to say approximately, or do you just say equals because it is eventually as it approaches infinity equal to 1/3? But you can never reach it, so it has to be like approximately.
Technically, we say the limit of S of n as n approaches infinity equals 1/3. And that gets us out of the conundrum that you're getting at, Eve, which is, can it ever actually get there? Well, I mean, if you added a new term every second, does it make sense? It doesn't make any difference. You still can't add them all up. So we say it approaches a limit of 1/3. We say it has a ceiling, and the ceiling is 1/3, but it gets away from the fact that you can't actually ever get 1/3. Does that make sense? Because you can't add infinitely many terms. You can't get it done. So mathematicians make the distinction of saying its limit is 1/3 instead of just saying S of infinity is 1/3. So we say, I hope this is becoming part of your language. We say, hey, this converges. It's convergent. It's not divergent. It's convergent. Converges. Not only that, we know what it is. One of the really disappointing parts of this class is we're going to be able to show that lots of series converge in this class, but we're not going to be able to figure out what they are. That's the crazy thing. There's some that we can, and the ones that we do are breathtakingly beautiful, but I can make up series that we can say converge, but then we would say, I don't know what it converges to. So anyway, we'll tackle that in more detail later on. Let's see. I wonder if I'm going to run out of paper. I think I am. I'm going to make a new piece of paper. So 10.3, we're spending 2 days on this. We're talking specifically about a series. So watch this. Let's say S of n equals, let's say 5 times 1/3 to the n power. And we're going to let n go from, let's see, where should we start? Let's start at 0 and go to, well, n. Notice I said go to n, not infinity. Now we could ask the question, what does that approach as n goes to infinity? Do you recognize this as a geometric series right now, even in this form? If I asked you for S of, I don't know, 64, would you agree that 64, that's really tedious? If I asked you for S of 6, would you say, well, I think I'll just add them. There's only 6 of them. I'm just going to add them up. Let's see, 5 times 1/3 to the 0 power. 1/3 of the 0 power is 1. So the first term is 5. And then the second term would be 5 times 1/3 to the first. That'd be 5/3. 5 times 1/3 to the second, that'd be 5/9. Hey, I see the patterns. 5 on the top every time, and the bottom just gets 3 times bigger. What is that, 243? So if you ask me for S of 6, again, that's code for the sum, S for sum, of the first 6 terms, not a list of the first 6 terms. I did not say A of 6. I didn't say give me a list of them. Would you agree that these are on the way, the individual terms on the way to 0? In other words, A of n is going to 0. The individual terms are going to 0. The sum's not going to 0, but the original terms are going to 0. The sum is clearly more than 5, right? Because the first term is 5 and the second term is more than 1. So it's like who knows what this is approaching, but so with 6 of them, you could just say, well, I'm just going to add them all up. But, what if we do go to 64? So in which case I kind of have to say, well, there's only so much paper. So bam, I'm done. Can you do what I just did a second ago? Do you recognize this as a geometric series now? If you didn't recognize it before, hey, look, everyone is just 1/3 times what it was before. Can you do the old, trick of multiplying this times both sides times 1/3? Well, do you see the multiplier is 1/3 here? So if I multiply both sides of that times 1/3, subtract those two equations, can you see what it adds up to? I'm going to give you a second just to do that because I think it's important to be able to do this manually to see it really simple.
The n on top of the summation symbol is kind of messing me up.
Let's see. Yeah, I can kind of see why you're saying that because I got n twice. Is that what you're saying?
Yeah.
Yeah, you're not wrong about that. I could say it like this, like k equals 0 to n, something like that. That'd be better. You're not wrong, Raymond.
Okay, that makes sense now.
Yeah, you're not wrong. That was a little.
Because I thought we would leave it at 0 the whole time. I didn't know that it would be able to increase.
Yeah. So the idea of the summation symbol is k is working its way from 0 to n, and it's getting there by landing on whole numbers.
Okay.
Thank you for pointing that out. I'm going to play for a second while you're coming up with what you think is an answer.
I got 7.5, but how you're doing your numbers is really messing me up because it looks like it's going to pass 7.5.
Yeah. Notice I literally listed the first few sums. So S of 0 is 5 since the first number on our list was 5, and then I added 5 plus 5/3 and got 6.66, and then S of 2. And by the way, notice, and I kind of screwed this up a minute ago, that right there is S of 2. You might look at that and say, well, isn't that 3? That's what I just did a minute ago. I said, wasn't that S of 6? But remember, it's a technicality, but I started at 0. So there's like one extra term. So S of 6 is actually the first 7 terms of the sequence added up. That's easy to screw up if you start at 0 like I did. So notice initially it grew pretty fast. It went from 5 to 6.66, but now it starts to look like it's, like Eve said, maybe it's on its way to 7.5. 7.5 looks like a reasonable answer, but it also looks like it might blow past that, like it might get a little over 7.5. But notice you can see it happening. I'm guessing 7.5 is the answer. So let's all prove it together. I'm just making up some other letter. I could call it S if I wanted to, but and then the key with this one though is you actually are ending at S of 64. 1/3 to the 64 power. Whew. I don't even know what that is. So I'm just going to write it out. I'm just going to cheat. I don't even know what that is. Seems like such a gigantic number that. So what happens if I multiply everything by the R value? 5 gets turned into 5/3. 5/3 gets turned into 5/9, and so on and so forth. Everything gets a third bigger. So that means the last term of this would have yet one more third than it used to have. Instead of 64, it's going to have 65. And so if I subtract in this direction, I have t minus 1/3 of t. And a whole bunch of cancellations happen. 5/3 minus 5/3. This term will cancel out with the one in front of that. And so all I have left, do you see this on the other side, is this 5 and that last term, which outgrew the previous list. That's the only terms that are left. So on the other side, I have 5 minus 5 times 1/3 to the 65th power. So on the left side, I have 1 minus 1/3 t. That'd be 2/3 t. On the right side, I don't think I have anything different just yet.
Wait, I'm confused. Why doesn't the 65th power cancel?
Because the
Are we not going to infinity?
Not yet. We're going just to 64.
Oh, okay.
We
I
will
was like,
we will
whoa.
be in a second. And so t, which is S of 64, is 5 minus 5 times 1/3 to the 65th power, all divided by 2/3 or times 3/2. And so, you know, again, that's just a cool shortcut, right? Like I made it to S of 6 by just, you know, busting out my calculator and go manual style. But to make it to 64, hey, that's kind of a cool shortcut. So, of course, I'm curious what that is. I mean, that's a reasonable number. 5 minus 5 times 1 divided by 3. Insert. And I'm curious, to Eve's point, whether this is going to make it over the top of 7.5. But when I divided that, interestingly, when I typed in just the top, it gave me 5. The reason is because 3 to the 65 power is such a gigantic number. I think my calculator kind of blew up. So 5 times 2/3 is the same as 5 times 3/2. Actually, my calculator thinks it's exactly 7.5, which it is not. So my calculator kind of blew up there. But yeah, what is if I sort of uncautiously write S of infinity here, what changes about this? If I was to redo that, what do you end up with? Or maybe I'll even be a little more precise and say S of n. What's the limit of this as n goes to infinity? What changes about this statement right here?
Would you lose the 5 times 1/3 to the 65?
Yeah. So notice nothing changes. Like you still have this 5 and you still have this t and you still have that 1/3 t. But this term right here, what is it?
Basically 0.
Yeah. You have 1/3 to the n power divided by 2/3. But what happens to 1/3 when it's to the infinite power? Well, that whole thing is on its way to 0. And so it really is 7.5. We saw it happening here. And then to Eve's point, I think it's surprising that even after 6 terms, it's already within 4/1000ths of its answer. It kind of feels like it might make it over the top of 7.5, but the numbers are getting small so quickly that it actually doesn't. And so this really does have a limit of 7.5. And we were already ridiculously close after just 6 terms, or actually should say 7, since S of 6 is really adding the first 7 terms. One little pattern I'll add to this that I don't think you really need to know. I'd rather you just do this manually, but for a geometric series, you'll see this in your book. For a geometric series where r is less than 1, technically, and greater than -1, as long as it's smaller, that means each term is going to get smaller because you're multiplying it by a percentage that's less than 1. Let's see, what's this pattern here? Well, you have this 5, which was kind of out front. Kind of this, I don't know what to call that, your A value or something like that. And this 1/3 is your R value. In the end, notice what happened to our formula. We ended up with on top the 5, or that A value, and on bottom, we ended up with 1 minus the R value. Like as a shortcut. Again, I'd prefer you just make this for yourself, but I will tell you that. This would be the limit as n goes to infinity. So we don't have to write that every single time. So that's kind of cool. So let me just play with that for a second. Let's see, a second ago, when we did that square problem, it wasn't multiplied by anything. Our R value was a 4th, right? But it was multiplied by 1, like there wasn't a 5 in front of it. It was just 1/4 raised to the k power. Excuse me. So it's kind of like there's a 1 out front. So let's see, was the answer to that 1/1 minus a 4th? Isn't that what this formula is saying? Is that true? Not true. Let's see, that would be 1 minus 1/4 would be 3/4. That would be 4/3. That's not what we got, right? Anybody know why?
Well, that
Isn't
one we
that-
started at 1 instead of 0, so maybe that has something to do with it.
Yeah, that's exactly right. We started at 1. If we started at 0, then it would have worked. In other words, this formula that I just gave you, it works if you start at 0. And that's why I think to some extent, it may be a little better just to do this manually every time, rather than kind of rely on a formula that you don't really understand well enough. I mean, you need to make it for yourself, but Ben's exactly right. So notice in this case, the A value is a fourth. So in other words, if we took the answer we just got a minute ago and multiplied it by a fourth, I'll erase this because it won't make any sense in the previous problem. But if you multiply that by a fourth, oh, look, it's a third. So, I mean, this formula does work. And so maybe I'll add to this, if and only if you start at K or N equals 0, that formula works. Okay, let's play a little bit. So just like a kind of a sort of a typical book example. It seems like it's time to change colors. Book example. Again, I can start any place I want here, but we're always going to have infinity now. I mean, that's the idea. This is calculus. It's never going to be, 1 to 60. It's never going to be that. It's always going to be infinity. We're done with just playing around with figuring out, the kind of the simple concept of what this is saying. The only question is, do I start at 0 or do I start at 1? Incidentally, could I start at 7? Sure. Doesn't make any difference what you start with. Matter of fact, I think I will start at a weird location. Start at 2. First of all, do you already see this as a geometric series?
Yes.
Do you see that R is less than 1? Hence, this is going to converge to something. Like I know that right now. And it's cool because it's geometric. Again, this is one of the few examples where we can actually answer the dang question. So again, I would encourage you to just keep this simple, write it out. And just use the little trick of multiplying by 3/8 and creating a new one. I don't like that formula above just because the fact that I didn't start at 0, then you're all handcuffed because all you do is just use some formula. Now it doesn't work. Or you spend your time trying to get K to start at 0 and rewrite this formula a little bit. Just write the dumb thing out. I think it's important that maybe you don't recognize yet that it's a geometric series. The letter S is a good choice. Sum. You're just summing this up. But it's infinite. you recognize that your R value, each term is just getting multiplied by 3/8, very visible in the original summation. So then you say, well, cool, then I'll just multiply by 3/8, which will create the same exact sequence or series, since I'm adding them, not sequence. So it just moves it over to the right. That 9/64 turns into 27 over 512. That 27 over 512 turns into 81 over 4096. Because this time it goes forever. Does it make sense? I don't need to write anything else. I mean, these dots are identical because they go forever. Is there technically one more term in the bottom? Well, yeah, there would be if we stopped, but we're not stopping. There's infinitely many, so they're identical. So now when I subtract, notice what happens. The pattern that I showed you a second ago, what happens is 1 minus 3/8 is 5/8 when I subtract. And all these terms go away. What doesn't go away? Just that first term right there. That's the only term that doesn't go away. So you end up with, hence S equals 9 over 64 times, not 5/8, but 8/5. Little canceling goes on and you end up with 9 over 40, I believe, which is a very, random decimal. When I bust out my machine and I divide 9 by 40, no, actually I did get a terminating decimal. I got 0.225. So we sort of got lucky in this case. If it had been 3/7, we wouldn't have got as lucky. It would have approached some random decimal. So this is the limit. It does converge. Not only that, we can even know what it converges to. That's pretty cool. Unnecessary, but for those of you who are sort of a little bit more theoretical types, is there a way that you could rewrite this sequence so it started at 0? That way you could use notice there's a 1 out in front of this. You could use the 1 over 1 minus R trick. Is there a way you could rewrite this? I can't just stick this up here. Can't just stick K up there, right? The first term still needs to be 9/64, doesn't it? How are you going to get that to happen?
Can you just put 9/64 in front? Because if you're going to 0, if K is 0, then it's 0, so that cancels. So you just put 9/64 in front.
I don't know. What do y'all think? There's Eve's idea. Does that work? That's right. So now could you use our, goofy little formula and say, oh, the formula is A, which we now figured out is 9 over 64 divided by 1 minus our multiplier 3/8. Hey, look, that produces the same answer. Notice it's exactly what just happened right there. But I'm just saying it took a little work. I mean, it takes work either way. I think it makes more sense just to do it logically. I mean, I kind of like writing it out like I did in blue, even though it's a little more time consuming. If you do this a bunch and you start to feel good about it, I don't care, like use the shortcut, but that's interesting. So some books, if you will spend all their time helping people remanipulate the equation so that it always starts at 0. That way you can just kind of use that little formula. But again, that's an example of the kind of person I would meet in the street 6 months from now and wouldn't be able to do one thing that we just did, because this, the memorized approach to that was real fresh for them while we were talking about it, but they didn't really understand it deeply. They didn't make the formula for themselves. And therefore 6 months from now, they know nothing. And so, I don't know, if stuff is hard, fine. But if it doesn't need to be hard, don't make it hard. To me, the blue algebra approach, Not hard. I'm going to be able to do that 6 months from now. In my case, I've taught this a lot of times, so I can, kind of do both, but just interesting.
So that 9/40, that's from when we started at 2. It wouldn't change if we started at 0 in the original equation.
We'd get a different answer if we started at 0. Yeah,
Okay, yeah.
we definitely would. Because then it would be 1 over 1 minus 3/8, which would be 5/8. And then 1 divided by 5/8 would be 8/5. So if we started at 0 here, the answer would be 8/5. So it does make a difference where you start. So what's going to happen with this one then? Second example.
That's gonna diverge
Why?
because the rate is over 1.
Yeah, do y'all see that? Each term's getting bigger and bigger and bigger. See, the key with R being smaller than 1 is that means each term gets smaller and smaller and smaller. In other words, A to the N is going to 0, but here each term is actually getting bigger and bigger and bigger. Do you see that? So the sequence from Thursday and Wednesday last week, the sequence is not approaching 0. If the sequence doesn't approach a 0, then good luck trying to add them all up because each term is bigger than the previous term, right? 8 divided by 7. What is 8 divided by 7? That's a weird decimal. It's like 1.14. 1.14 represents 14% growth. So that means each term is getting 14% bigger than the previous term. So the terms are getting bigger and bigger and bigger. There's no way this is going to add up to something then. Now, could you still answer the question using the same technique we just did? We're not going to do this, but could you still answer, S to the 19? Could you still answer that? Yeah, well, there's only 19 terms. Could you answer, this? Sure. As long as that's not infinity, you can answer it. And the technique that we just talked about would do it. So you can give finite answers to this question, but again, we're not really doing that anymore. But this is going to converge because the sequence does not approach 0. Interesting question. What if we started somewhere else? What if we didn't start at 0, but we started way out there at 1,000? Does that help? Now does it converge? Doesn't make any difference. Really doesn't make any difference where you start. The terms are getting bigger no matter where you start. 8 over 7 to the 1,000th power is probably a pretty huge number. So you're just starting at a larger number. So that doesn't actually really help. So this is going to, in the language of your homework assignment, does not exist. I don't know. Books usually say diverge or infinity or something like that. Diverge is probably the worst word just because you got to actually learn the meaning of the word in order to use it.
Will we be going to negative infinity?
Good question. Yeah, could you have negative numbers? Let's try that. What if it was like -2/5 or something like that? Just let's get the negative inside there. Why is that a little weird that it's negative? What's going to happen when you start putting the terms out?
Doesn't this oscillate? Is that the right word?
Yeah, like when you square this, don't you get a positive number? So it's like you don't just get negative, negative, negative all added together. Now you're going to have a negative and a positive. And so, yeah, maybe Eve is right. Like you're going to have a positive number, then a negative number, then a positive number. So again, I don't think this is obvious. Like play with it, write it out. Like this isn't hard.
But doesn't this equation converge because it's less than 1?
Yeah, notice it's still less than 1. So the terms will get smaller. So a to the n is on its way to 0. Since that r value, the multiplier this time of 2/5, is less than 1. So the terms are going to 0. So it sort of does feel like it should add up to something. It should converge to something. And you might wonder, is it still geometric? Is it still a geometric sequence? Because every other number is going to be positive now and every other number is going to be negative. And so anyway, play with it for a second. Let me just give you a second to think about it. Notice I started at 1, so you can't use that little formula as a cheat. But you could potentially change it to k is 0 and mess with the expression, but just do it blue collar, write it out. I just wrote out the first few terms if it's helpful to you. I just wrote out the first 5 sums. It does appear to be approaching something. My first thought was, oh, it's surprising it isn't oscillating because it stayed negative the whole time, but it is oscillating. Do you see that? Was your thought the same as mine? Oh, it's negative every time and they're getting smaller. It's not oscillating, it's monotonic. But it is oscillating. Do you see that? because it started at negative 0.4 and then it went all the way down to negative 0.24, but then it actually went back up to 0.3, back down to 0.27, back up to 0.28. It actually is wobbling its way. Now it's wobbling down there below the x-axis at negative numbers. But this is oscillating. Again, I don't know if that's inordinately important, but mathematicians thought it should be pointed out. Does the normal, the thing you were working on, does the normal rule of just multiplying by 2/5 and, you know, subtracting two equations, does that work? Does it give you an answer? Does your answer make sense with the first 5 terms that I just tried?
I think so. I got let's see, let me make it a fraction. -2/7.
You got -2/7.
Yeah.
So as a decimal, 2 divided by 7 is 0.285. That looks reasonable. I can see it landing there. So let's see if you're right. So let's see, what do I multiply by? Well, you know, again, each term is being multiplied not by 2/5, but by -2/5. And so if I took my s and multiplied by -2/5, then this first term, -2/5 times -2/5, would indeed be 4/25. And the next term would be -8 1/25. And the next term would indeed be positive 16/625, and so forth. So interesting. Seems like it didn't matter. The fact that it was negative looked weird, but it seemed like it didn't matter. So if I subtract, as we did before, these two equations, then gone, 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 everything's gone. So I end up with 1s minus 2/5 s. Hey, wait a second. That's 1 minus a -2/5 s, isn't it? It's not 1 minus 2/5. It's 1 minus a -2/5, which is actually 7/5. And on the other side, I have -2/5. Hence, s equals -2/5 times not 7/5, but 5/7. I agree with you, Raymond. So s does appear to approach the limit of -2/7. So indeed it does converge. Not only does it converge, we even know what it converges to. That is awesome. So it didn't really matter. Isn't that kind of cool? Didn't make any difference that what one was negative. Still worked just.
So, out of curiosity, when R, we say that R converges when it's larger than -1 and less than 1.
Yeah.
So if we're dealing with negative numbers, would it diverge if it's smaller than -1?
That's right. So if it was like -8/7, the numbers are still getting larger. Now they're getting larger negatively, but it's going to go off to negative infinity. One of you asked that question, or I think earlier, is it possible for something to go off to negative infinity? Yeah, it looks like if we took this to like -8/7 and we said, what happens then? It looks like it's going to probably go off to negative infinity. So it will diverge and you can go to negative. So yeah, awesome.
Would that be going to positive and negative infinity though? Because it would kind of be like going increasing like.
Yeah, notice it's not obvious. I find the same thing I find here, which is I sort of feel like I need to play with that a little bit. I guess I'm just saying it's possible that it would go off to negative infinity. But the terms are going to get larger and larger and larger. So either way, yeah, I mean, I got to play with that. I'm not exactly sure. My gut is it goes to negative infinity, but I'm not. I'm going to have to play with it.
So what do we do with terms that we can't like converge, but we can't find the answer?
Yeah. Oh man, that's going to bug you to death. It's going to bug me to death too. What do you think about? I got this one in my back pocket that I want to show you. I'll probably show you today just because it's so cool. I can't wait to show you. But Let's do one more sort of, I don't know if the right word is easy, but let's do one more easier question. And then I think I will say something about that, Eve. So I've been pretty nice up to this point, but what happens with this guy? What if I said from k equals 0 to infinity, but the expression was e to the negative 2k? Uh-oh. Does this converge? Sort of your first question, is it converge or diverge? And of course, if it diverges, fine, we're done, goes to infinity. If it converges, then the second question is, can we know what it is? And that's Eve's question. So what happens here? Again, I don't think this is obvious. I just want to give you a second to play with it. If you didn't notice this already, make sure you see that an easier way to write this out, since it's a negative exponent, is just to think of it as 1 over e to the 2k, so it isn't as confusing looking. If you didn't establish that earlier, do that now.
Alan Whitney.
Man, you gotta leave me alone, dude. Just to check yourself, did you get what I got? Did you recognize, oh, that's what this says? That's not that complicated. E to the 0 is just 1. Perhaps I can write that e to the 0, which is actually 1. I'm a little interested in your intuition. Does this feel to you like it will converge?
Well, it's got a 1, and then everything after that quickly goes to 0.
Yeah, e to the 6th is a big number. Like, what is that? E raised to the 6th. E raised to the 6th is like 403. So by the time we're at the 4th term, it's already 1 over 403. That's a really tiny number. And the next term is even going to be worse. It's going to be 1 over 2980. Does this feel to you like it's going to converge? That's what I'm getting at. Can you see that it's like, yeah, it feels like that's going to converge. because the terms are not just going to zero, but they're going there fast. Can we figure out what it is though? Can we see what this actually converges to? What's the answer to that question? Can we?
Can we write the rate without being in terms of k?
Yeah. What's the recursive definition? What are you doing? Like, what's the pattern? What's the next term? Like, can you see what's happening here? How are you jumping from term to term? Maybe that wasn't obvious before, but maybe once I write it out in blue, now it is obvious. What are you doing going from term to term?
Multiplying by e to the 2. I mean 1 over e to the 2. So e to the negative 2.
Yeah, aren't you multiplying by 1 over e to the 2 every time? What does that make? What does that mean this series is?
Geometric?
Still geometric. Now it doesn't have a nice fraction like, 1/4 or 3/4, but it's like every term is found by multiplying each term by something. And notice, what is that multiplier? Well, 1 over e squared. What's 1 over e squared? 1 divided by e raised to the second power. That's 0.13. This multiplier is not a nice fraction, but it's less than 1. I mean, r is less than 1. This is going to converge. This is just a geometric series. Just doesn't look as nice, doesn't look as normal, doesn't look as recognizable as all the examples I gave before. So yeah, this is easy. Not only that, I started at 0. So you could even use that shortcut little formula if you wanted to. I'm not going to use it. So yeah, this is nothing new, which is, again, I would say not obvious. So if this is geometric, then I could just multiply it by my multiplier and recreate the same exact series. No different. That's why geometric is so important, because I can recreate the same exact series by just multiplying both sides by something. Once that's done, easy. Now I can subtract them, and then I won't have infinity anymore. Subtraction gets rid of infinity. Gone, gone, gone. So I have s, to be a little more careful here, s of n minus 1 over e squared s of n equals, well, the only thing left up there is that term, which was actually just 1. So again, I struggle a little more with something that looks so weird. I see these both have an s of n, so I'm going to factor it out. Kind of got to let my algebra skills work a little more. I don't see it as easy, right? Neither do you. I don't see it as easy as I did with kind of just ordinary fractions. So I'm factoring an s of n out. So that means s of n, the sum, is actually approaching this. Now, could you clean that mess up a little bit? I don't know, maybe. If I multiplied top and bottom by e squared.
That equals a cleaner version in your terms, e to the 2 divided by e to the 2 minus 1.
Yeah, I'd say that was worth doing. If I multiplied the top and the bottom times e squared. Do you see why I did that? A lot of people's algebra skills, usually by the time you get through calculus, your algebra skills have grown, but it's like, I don't like fractions over fractions. That's really confusing. So since the denominator is e squared in that bottom fraction down there, then I think, well, if I multiplied top and bottom by that, then it'd be gone. And And notice that's a decimal of unrecognizable, like you never would have guessed it, right? Like if we had got out Excel and just added up, the first 1,000 terms and said, yeah, it looks like it's converging to something, but whatever decimal that represents, it's not like we would have looked at it and go, I think I recognize that. Isn't that e squared over e squared minus 1? Like you never would recognize this, right? So this actually was just a geometric series. It wasn't actually near as hard as it looked.
Yeah, when I put that into my calculator, I get 1.156 and a bunch of other stuff at the end. And that's what I got when I did the multiplying by 1 over e squared and subtracting.
Yeah, notice because this one started at 0. Again, I'm just kind of wondering if our formula works. It started at 0, and notice there's nothing in front of it. There's a 1 in front of e to the -2. So does our formula work where we go, oh, it's 1 over 1 minus our multiplier? Well, apparently, because that's what we just wrote a second ago. So, the shortcut's worth something. I'm not going to completely throw it out. That's kind of cool that it produced it that fast. But again, I personally get a rise out of just being able to figure this out myself, or not need me help.
On a test, could we say that we used the formula?
Yeah, you could. Just show that, like just write a over 1 minus r and work it out.
Okay.
But again, my warning in that is notice that only works because we started at 0 here, right?
Yeah.
So if we didn't, you'd have to, then your work would be modifying it so that it did start at 0. And a lot of these problems do. I mean, a lot of them start at 0, so that's kind of cool. I won't take the time to do this, but I'm very, very tempted to, go over to Excel and, watch that happening. Watch that number approaching that. Actually, I'm going to give into the temptation because I want to look and see, is it monotonic or is it oscillating? And so yeah, do take note that decimal, if you write it on your calculator, is like 1.1565 and so forth. But let's just play with that for a second, because I just think it's amazing. I've said this before, but it's amazing that we live in a world where we don't have to do this near as theoretically as anybody in history prior to us. They didn't have the ability to add the first 100 terms of this. Remember, they didn't even have a calculator, let alone, a spreadsheet. So there's the first few terms. What am I doing? I'm taking that first term and plugging it into the expression 1 over e to the 2k, or just e to the -2k. In Excel, I showed you this the other day, but there's no such thing as e. You have to say exp for exponential. And then you don't raise it to the power, you just say exp, and then you put in parentheses raised to the -2, and you have to say times that other number over there. So notice it worked. So does it still work here? This is 1 over e squared. If I myself wanting to check my work, so if I say 1 on my calculator divided by e raised to the 2nd power, yeah, 0.135, it's working. So the first test here is just, are the terms going to 0? Oh, look, they're going to 0 darn fast. Again, do you recognize scientific notation there? That's 2.6 with the decimal point moved 23 places to the left. Whoa.
Yep.
They're going to 0 fast. And now I can just kind of grab all these and cheat. And down here in the corner, notice it says the sum of just those first, notice 27 numbers. That's not 26, that's 27 because you start at 0. So S of 26, which is actually 27 numbers, is 1.156. Like, it's working. You see what I'm saying? I can see it on its way to the exact value that we thought. Here's something kind of cool too, just as kind of a neat shortcut, but watch this. if I say this cell is going to equal sum of these two cells added together, notice it puts a colon between them. So then there's the sum of the first two numbers. But I always want to start at F3. So if I put dollar signs in front of those, that's not right. If I put dollar signs in front of those, come on, man. Then if I drag this down, notice that becomes F3 to F5, which means add F3 plus F4 plus F5. So then this is S2 and this is S3 and that's S4. So a second ago, I manually wrote out the first few terms. And so this is kind of cool too. Notice you can see this already approaching. Notice this next term is so small that you're kind of adding nothing. Like we're already almost there and we've only added the first few terms together. But notice it's very clear again that this is approaching a limit because it already is accurate to 6 decimal places after just like first 7 terms. Excel's more powerful than your calculator because you can actually ask it for more decimal places. Increase. Isn't that right? Increase. Decrease. Why isn't that working? I'm going to say format cells, go to number, and how many decimal places can I get? I'm going to get asked for as many as I can. I'm going to have to go until it says no more. Well, maybe I won't. Yeah, 30. Can have 30 decimal places. Notice it doesn't seem to be able to handle that because those wouldn't all be zeros. But that's more than your calculator. Well, a little more because this, as I said, it didn't seem to be able to handle it. But notice it's not even changing from here on. Like those answers are all fixed. But again, can you see the calculator has exploded at this point? Like it just can't deal with this. These numbers are so tiny that it just can't work. So that's the beauty, if you will, of the theory. We're literally saying we know the exact answer to this. 1e squared over e squared minus 1 or whatever we said it was. But the point is, we can watch this manually happening to kind of make sure we can hypothesize that this is going to converge, even if we don't know what it is. So I think that's extremely cool. So because of the utterly essential nature of this section, in one sense, I could say we're done right now, but there is one other weird sequence that your book calls a telescoping sequence that we'll talk about tomorrow. There's one other type of sequence that, series, we're adding them, so it's a series. There's one other type of series that you can actually add up and get the answer to. And what I'm going to do is quickly introduce it to you, but then we'll just play with it tomorrow. So I'll say even here tomorrow. What about this one? Let's see. No, we don't want to start at 0 because that would mean it would have 0 on the bottom. We want to start at 1. Does this add up to something? Now it's getting nasty. First of all, let's just play with it for a second. Let's see, what would it be? Well, if I put 1 in, it'd be 4 over 1 times 2. So that'd be 4 over 2. The next term would be, if I switch to 2, notice it becomes 2 and 3. So it's like the first one was 1 times 2. This one's 2 times 3. The next one is 3 times 4. The next one is 4 times 5. Do you agree with that? Do you agree that that's the pattern? Extremely important. What's your intuition? Do you think this will converge? What's happening to the terms? Are they getting smaller? Yeah, are they getting small pretty fast? I mean, it won't be long and I'll be out there at 4 divided by 9 times 10, right? Which is 4 over 90. That's a pretty small term. It's 0.04.
I think that will converge to something.
But do you notice it's not geometric? Look at the terms. The 4 is on the top every single time. So would you agree that here it's like, oh, I multiplied by 3, really a third. But then did I multiply by 3 going here? No, it was like 2. And then this is like not even, some fraction or something like that. You see, it's not geometric. So our little trick, like, isn't going to work anymore. So I would agree with you if you took that position that this does look like it's can converge, but we're kind of in trouble. Do you agree with that? Like, how are we supposed to figure out what this is now? And so this is a unique one. Tomorrow we're actually going to be able to get the answer to this one, but there aren't very many that you can. I'd encourage you, I want to shut up and get you out of here on time for a change, but I'd encourage you to go into Excel and just for a second, play with this. If you got 2 minutes, like go in there and generate in Excel and add those terms up and kind of see, does it look like it's approaching something, and try to get an answer. If you're lucky, maybe it'll approach something like 5, or something where it's like a whole number and it really does look like it's going to 5. That's what I'll start with tomorrow. I'll get Excel out and we'll kind of add them all up and, add up the first 100 of them and kind of see, does it look like it's approaching something? And I think we'll be convinced, yeah, it actually does look like it's approaching something. I hope it approaches some weird decimal so that we look at it and go, I don't know what that is, 3.9842667. And we're like, kind of like the E thing, like you never would have known what the exact answer to it was, but it looked like it was approaching 1.15. I'm hoping the same thing happens here. Notice we're already at 2 though. 4 over 2 is 2. We're already at 2 from the first term, and then it's 2/3. So we're already at 2.66. And then we're adding another third. We're already at 3 just right here. Do you agree with that? That's already 3 right there. So the answer is more than 3. So the question is it going to make it to 4? Is it going to land someplace in between 3 and 4? Maybe it'll land on pi. Pi is between 3 and 4. Maybe it'll land some recognizable decimal with some, just weird fraction, like since it's over 3, is it like 22 over 7 or 23 over 7 or some weird number like that. But mathematicians will call this a telescoping sequence, and I'll show you why tomorrow. But that is enough for today. All right. Disappear yourself. Stay after.
Bye. Thanks, Doug.
Thank you all.
Thank you.
See you tomorrow.
See you tomorrow.
Oh, one question I had.
Go ahead.
Did we learn all the material to start the 10.3 homework?
Yes, except for because of what I just introduced, there'll be some problems that you can't answer just yet.
Okay.
But there's a bunch of it you can do. Yeah.
Okay, cool.
Good
Okay,
question.
thank you.
See ya.